source build that thing, and then we go to build 0, and then we hit this, right? Array bounds check failed. Get up in GDB. Sig trap, it's hosed. So first of all, let's look where we're at. We hard code the positions of the player and the enemy, and then we call map path to, because we want to get this is from, I think, yeah, from and to. So we want to get the path via a star from the enemy to the player. So we call min heapify. So in the case where we only have one element in the heap, which is the case right now, we go to the end of the heap, which is actually the beginning of the heap, because size is going to be 1. So 1 minus 1 is 0. And so we basically overwrite h at the heap data, the 0th element of the heap, with the 0th element of the heap. That's not actually a problem because we decrement the size. Now the size is 0. And then we go into min heapify. The size is 0, and we get the left and the right of 0. So I might just need to add an early out. Like we could probably solve this by adding an early out here. Like if h dot size less than or equal to 0, then return. If the heap size is for whatever reason less than 0, certainly if it is 0, there's nothing to min heapify, so just return. So I'll compile and run that and see what happens. So we survived. Like God knows what's in our data structures. We don't return anything from path to. So we build these data structures, but we don't return anything. So there's really nothing to inspect. The reason I stuck with a heap that has U64 elements is because I didn't want to put math vector in it. But to remind ourselves of what a math vector is, it's 2 floats. And these floats are 4 bytes each. They're 32 bits, 4 bytes, which is a total of 8 bytes. And a U64 is also 8 bytes. So actually stuffing math vector 2f in here is not, there's no appreciable cost difference, assuming the alignment works out. And that would probably prevent us from doing as many transformations. What we need to do right now is actually inspect the contents of our hash table. There might be a convenient way to print the hash table. That would be interesting to print the hash table. And if we can get something pretty printed, then we can store vectors instead of tile indices. Well, let's just try and print the hash table and see what happens. That's the fastest way to check. %s, and we will say cost, nope, came from. Wow, that's pretty sick. Okay, I don't know how we can pretty print it, but this is useful. Oh, did I put an S in there? I put a %s. Still used to C and C++ or whatever. Oh, it's a hash table though. So we're gonna see a bunch of gaps, right? Well, we can just write a for loop, right? We can just write a for loop to print the stuff, like for key value. Let me print the key and the value. Undeclared identifier for expansion. Oh wait, for expansion. Wait, look at this. Wait, does it? I wonder if it has to do with namespacing though. For expansion must be overloaded. So I wonder if this is like an operator. Here, we can try this, right? For expansion gets hash table for expansion. Yes, okay, yo. Okay, so the good news is we can print, right? This is came from, so we're saying 357. I can't understand any of this at all. So let's actually switch the storage to use vector. Yeah, I'll go on a little small expository detour, right? So what we do here when we get neighbors is we set up storage in the caller scope for the return value of neighbor, not the return value, but rather a buffer that neighbors writes into. And we do this so that way we can get a view. We can return a view, neighbor's view, right? But if we go into neighbors here, like what I wanted to do was I wanted to return a view here. And I wanted this view to be over storage that neighbors sets up. And obviously if neighbors sets up storage in its stack, then once we return from neighbors, we could return a view to something that existed in our stack that we set up, to a local basically, but obviously that's an invalid program. That's a bug because the storage goes away. The view itself is valid as far as usability is concerned, but logically what it points to we no longer necessarily own, or rather the lifetime is over. So we basically pass in a buffer here, the ghetto named buffer here. And then n gets _n. This creates a view over the backing buffer. Another thing that we could do, I was thinking, was actually set up storage here and then return the storage. And I was thinking about this morning. I'd have to do a test, but I'm pretty sure this would also be a bug. What you'd have to do is return a view and return the underlying storage. The reason you'd have to return the underlying storage is so that way its lifetime survives. But the underlying storage, or rather, excuse me, rather the view, right? The view's data member is a pointer. And the question is, if it points to space that was allocated on this stack here, then the view is still invalid. The backing memory was copied to another return value, and that's valid. But what we basically want is a view that allows us to index into storage returned from this function. I'd have to do an experiment to see if that's how Jai works. I'm not entirely sure how to point one return value at memory for another return value. Like, I don't know if that's available until the function starts to return in not the prologue, what do you call it? Like the trailer of the function or whatever. So for now, we just pass in the buffer. We don't need world tile to index anymore. We just say up and down and left and right. But now we have to go to the call site, and this is going to be vector 2f. We don't need to call this because we already have tiles. Good, so we're getting rid of like a ton of transformations here. This is great. Attempt to use the binary operator, which is not defined in the scope for these types. Okay, so it's operator. This gets math. That should solve that. That did not solve that. Why did that not solve that? This is complaining from hash table Jai. Okay, the good news is there's a given compare function. So I think I just need to pass that into the initializer, right? Given compare function is math operator. Now that did not work. Cost, now it's cost so far. Hash get hash. Procedure call did not match any of the possible. Okay, so I need a hash function. So we have a vector which is just two floats, right? So let's think about uniqueness of a vector. X comma y, if you have 0 comma 1, that is unique when compared to 1 comma 0. But if I hash 0 and I hash 1 and I add them together, this does not work. We know that there is a hash function for U64. What we can do is join the float 32 and the float 32, right? We'll build a U64 out of them. We'll hash that. That will preserve uniqueness of order of X and Y. So X and Y, if you transpose those, yeah, you preserve the uniqueness of 0, 1, and 1, 0. The idea is if you have hash data A, then you can combine A with some new data B by passing the hash from A in as the H parameter to B. Okay, well, so we could also leverage that, I think, to preserve uniqueness. Like this is the H parameter they were talking about earlier. We're not going to be chaining hashes together. We're going to be just doing a single hash. Hash is going to take the vector 2f, and this returns a U32, I guess. Combined is going to be a.x shifted up by 4, ORed with, I've probably got to go to U64 first, right? We don't want to shift off the bounds of the type. So first we widen the type, widen the storage to U64. We shift the lower 4 bytes up by 4, and then we OR this with a U64 a.y, and then this all needs to be, or this is a bit shift though, that's the problem. Okay, so I'm doing this wrong, this is a bit shift. So what you want to do is shift by 32, right? So shift by half the width, and then we OR in on the bottom 32 bits a.y, and then we return the hash of combined. It's hash.get hash of combined. Given hash function is math.hash. Okay, that didn't do much. Left argument of a shift operation must be of an integer type. Whoa, okay, so that tells me that the cast is actually lower precedence. Thank you, compiler. Okay, we got that building, we run this, cursory glance. Basically, any of these things should only be off by the other by 1. Like the value should be off from the key by 1 in all cases. And it looks fine to me, right? Just a cursory glance, it looks okay. The whole purpose of this is to select the next tile to move to. Select the next tile to move to for some entity, because we want one entity to go to some destination, right? But they only move by 1 tile on each unique movement. So from the enemy to me, basically reconstruct the shortest path. Once we reconstruct the shortest path, we have a path, for lack of a better term, through the data structure that shows us how to get from A to B. And the only thing we actually use in the end is the very first step in that path, because we're only taking 1 step at a time. I guess we could take multiple steps as well, depending on scaling of movement speeds. We have to actually rebuild the full path in order to figure out what the correct first element to pick is. So for simplicity, we'll just return a single tile, so that way we can advance the enemy, and the enemy will basically chase us. Exists and from iter is going to be hash table dot table find cost so far, and then 2. So we start looking the path up in reverse. While from iter is not equal to from. So we'll also need an array, because we'll need to be pushing some of these values onto the array. You know, I don't think we need an array, in fact, right? Because basically we iterate through the table until we find from as a value, and then we just return the key, because the key is the destination. From iter is just a terrible name here. Yeah, the names are still all backwards in here. These variable names are confusing me. I'll figure out a better. Let's see, since we're not building an array here, basically we need to save off intermediate values as we march along the path. So we say I went to, assuming that I start at 2 and the destination is 1 hop away, then I immediately set went to tile. I always set went to tile to from, because that is where, that's the destination we're going to try and take a step towards. Then what I do is I'm looking up the path in reverse. So I look at the destination and I say, how do we get to the destination? Well, we came from a specific tile. If the tile we came from is not where we started, then we need to take another look. So we need to advance our step. We went to a specific tile. That's where we came from. And then we update came from by saying, where did came from came from? So now we return a math vector to f, this guy here. This is going to be exists. Let's just see if this actually runs without dying. Okay, so this did run without dying. That's good news. Now I need to undo all this debug stuff. And let's just look at his position and the candidate position here. So the candidate position is always 1 away from his position, which is good. Now he wanted to move in Y. He wanted to move down in Y, which would be approaching me because I'm at 17, he's at 10, he wants to go to 11. That makes sense. He can only move in X or Y, but not both right now, right? Because we don't support diagonals. So if I approach him, right now I'm at 2013, he's at 2213, he wants to be at 2113. Yeah, this seems reasonable. So what we can actually do now, we get the path to this and we get the proposed direction. This direction is going to be wrong, or it's not always going to be right, is what I should say. So he should be approaching us, and he's chasing us, indeed. Eventually he'll catch us. I can't really put too much, well, maybe. Let's see. Oh, I can move diagonal. Right, I can move diagonal, but he can't. So actually I can outrun him. All right, well, look, he chases, and he's caught us. Whoa, look at that. That was interesting. He like ran away from us for a second. Oh, no, he didn't run away from us. No, or I could be tricking myself, but I think I just went diagonal and he went down like I'm doing right now. I can run diagonal to the left, but actually all we have to do, in fact, is support diagonal movement for him. Like the feature is incomplete. For example, if there is no path, you cannot discover my player's position from the enemy's position, something bad will happen. I think we will basically just loop forever. We're just going to loop forever, essentially. So we need to robustify this. Like if the enemy's right there, I can actually cut, right? Boom, I can cut. And that's kind of a weird mechanic in this tile game. If I want to, then we'll implement jump point search here. This works really well for us because, right, it's an optimization to the A-star search algorithm for uniform cost grids. And that isn't exactly what we have right now. Because if you remember down here, we have the single tile movement cost. We don't have any terrain cost or movement cost. The cost of moving diagonal is going to be less than the cost of the single tile movement cost, though. So I do need to figure out whether or not we are still a candidate for jump point search. Thanks for tuning in. I'm going to cut it here, clean up the code, probably off stream, and then we'll catch you guys in the next one. Peace.